Good morning friends, I welcome you to my channel Educational Information for All. I request you to subscribe my channel and hit the bell icon for new video notification. So today we discuss regarding intraparticle diffusion model. The aforementioned models can now describe the diffusion mechanism of the solute into the interior of the sorbent. The experimental data is usually fitted with intraparticle diffusion equation to observe the diffusion process. Intra-particle diffusion model is used to test the role of diffusion as the rate controlling step in the sorption process. It is an empirically found functional relationship. It is commonly observed for most of the sorption process. It is anticipated that uptake varies almost proportionally with the square root of time t raised to 1 by 2 rather than with the contact time. Diffusion in the bulk solution, then diffusion across the thin film surrounding the adsorbent particles, followed by intraparticle diffusion and adsorption within the particles. If the rate limiting step is the intraparticle diffusion, then amount of adsorbed at any time should be directly proportional to the square root of the contact time t. The chemical potential of the sorbent metal interactions were found to have the upper hand in controlling the mass transfer compared to physical mechanisms like pore filling or intra-film diffusion. On the basis of the change in availability of metal ion concentration over a period of time, the significance of intraparticle diffusion was analyzed by estimating the model constants Kp from the slope of the plots of Qt versus t raised to 1 by 2, that is square root t. Based on the theory proposed, intraparticle diffusion model is defined as Weber and Morris in 1962, that is give formula Qt equal to F into square root of t. Qt equal to Kp t raised to 1 by 2 plus C. Here Qt is unit of milligram per gram. We can say the amount of heavy metal adsorbed on the adsorbent at time t. T is the minute, it is the contact time. Kp, the unit will be milligram per gram into minute raised to 1 by 2. The interparticle diffusion rate constant is Kp. C is the thickness of the boundary layer. And we can find out the slope and intercept by drawing the graph Qt versus t raised to 1 by 2. Here formula will be, you can compare with y equal to mx plus c. From that we can get intercept c and slope kp. The large the slope indicates the high external resistance. Kp and c obtained from graph Qt versus t raised to 1 by 2. The value of Kp can be calculated from the slope. The higher value of Kp illustrates an enhancement in the rate of adsorption. C gives an idea about the thickness of the boundary layer. That is, the larger the intercept, the greater the boundary layer effect. If intraparticle diffusion occurs, then Qt versus t raised to half will be linear. If the linear plot passes through the origin, then the rate limiting process is governed by the intraparticle diffusion. That is, particle diffusion is involved in the rate controlling step. The linear plot did not pass through the origin, suggesting that the intraparticle diffusion is not the rate controlling step for over almost transfer of adsorption process. Some other mechanism along with intraparticle diffusion is also involved in the sorption process. The value of the constant C for all the three cations generally increase with increasing initial concentrations of the solution. This trend is expected due to the greater driving force of sorbent cations. increase in effective number of collisions between cations and active sites at higher concentrations. The first step or stage you can say for intraparticle diffusion plots, the first steeper region represents the immediate sorption or external surface sorption. The larger slopes of the first sharp section represent the external surface adsorption and show that in the beginning higher rate of metal ion removal is due to the immediate availability of larger surface area and active adsorption sites. Sharper portion is the external surface adsorption or instantaneous adsorption stage. The initial portion represents instantaneous adsorption stage followed by the gradual adsorption stage where intraparticle diffusion seems to be rate controlling stage 2. Now you can see here second step or stage. The second reason, which is the gradual adsorption stage, reflects that intraparticle diffusion is the rate limiting step. The second portion is the gradual adsorption stage where intraparticle diffusion is rate controlled. In third step or stage you can say the final equilibrium stage where intraparticle diffusion starts to slow down due to extremely low adsorbate solute concentration in the solution. Intraparticle diffusion starts to slow down due to low sorbate concentrations remaining in the solution. This indicates that transport of metal ions from the solution, you can see through the sorbent liquid interface to the availability surface of the sorbent as well as to the micropores may be responsible for the high uptake of metal ions. In general, the slope of the line in stage 2 is called an intraparticle diffusion rate constant, you can say Kp. The three chronological steps in the adsorption are film diffusion, particle diffusion, and absorption. At the initial stage, the adsorbate ions travel towards the exterior surface of the adsorbent, which is termed as film diffusion. After small fraction of adsorbate attaches onto the outside surface of the adsorbent, particle diffusion starts in the adsorbate ions travel within the pores of the adsorbent. The final stage is termed as absorption where adsorbate ions attach themselves inside the interior surface of the sorbent. The final stage or third step is generally very rapid, thus it cannot be treated as rate limiting step. If the external transport greater than internal transport, rate is governed by the particle diffusion. If the external transport less than internal transport, rate is governed by film diffusion. If the external transport is equal to internal transport, the transport of adsorbate ions to the boundary may not be promising at not worthy rate. So you can see the diagram where aqueous solution, boundary layer and porous adsorbent are taken here. This is the bulk transport of solute. One enters into the next film diffusion of the solute and next it is be intraparticle diffusion or pore diffusion. So this is the figure shows steps in adsorption process. Thank you.